All right, we're going to talk about a special kind of substitution that we can do that takes into account the fact that we know some trigonometric identities and trigonometric facts that are not part of normal algebra. This first part is really just normal substitution in the presence of knowing a couple of things about how trig functions are related to each other. But the reason we do it is because there's another form of substitution that looks and feels a little different than what we did before. And it mostly comes up in the context of trigonometric functions, but it doesn't have to. So first things first. In this problem, we're trying to find the integral of sine squared of x cosine of the fifth of x. And the main thing here to remember is that we have trig identities that tell us how sine squared and cosine squared are related to each other. So we know sine squared x plus so sine squared equals sine squared plus cosine squared equals 1. What this means is that I can relate sine and cosine through a substitution where I can substitute 1 minus sine squared for cosine squared or vice versa. So that means that if I have even powers of sines or cosines that I'm trying to substitute, I can replace those with expressions involving the other function. So in this case, once I have this identity, I can derive other identities for other even powers. If I want to know what cosine to the fourth is, please be careful that you don't just say it's 1 minus sine to the fourth. That doesn't follow. What we can do to get an identity for cosine to the fourth is take the identity that we just wrote and just square both sides. If you have cosine squared and you square it, you get cosine to the fourth. On the other side, you don't get 1 minus sine to the fourth. You just get 1 minus sine squared squared. So you literally square that side. Similarly, if I wanted an identity for cosine to the sixth, that would be taking this original relationship I have here and raising both sides to the third power. Cosine squared to the third power will be cosine to the sixth, and on the other side I'd have 1 minus sine squared x cubed. So that's really the only thing really going on the problems in section 7.3, at least the ones that we will do for our class in this somewhat abbreviated final month. So in this problem, I have sine squared x times cosine of the fifth of x. And my first step here is going to be to rewrite this, and this will seem a little silly. So the only rewrite that I've done here is changing cosine of the fifth to be cosine of the fourth times cosine. My reason for doing this is that cosine of x dx, when I do a substitution, if I let u equal sine x, then du will be cosine x dx. And so that's the substitution that I'm going to be aiming to do. The substitution u equals sine x du equals cosine x dx. That'll be my goal. And so this seems like it's going to work fairly well. The cosine x dx here part here, we see that sitting there. That will become du. Sine squared x will become u squared. And then the mystery part is what happens to this, because it's somewhere in between. It's not exactly u and it's not exactly du. Well, because that is cosine to the fourth, cosine to an even power, then I can come back over here and find a relationship using the trig functions that allow me to change cosine to the fourth into an expression involving sine. And so that's what I'm going to do in my next step. Before I actually do the substitution, I'm going to take one more step where I rewrite cosine to the fourth as 1 minus sine squared squared. And then I still have cosine x dx. So all I've done here is rewritten this as this using that fact. Now it's the case that everything in this integral, sine squared becomes u squared from the substitution. Sine squared becomes u squared, and cosine x dx becomes du. So just like I anticipated up here, but I'm not getting stuck here because I can rewrite that in terms of sine. To actually do that integral the rest of the way, to figure out what that is, I would need to basically just multiply this thing out. 1 minus u squared squared, that can be multiplied out by FOIL. So I have u squared times 1 minus u squared times 1 minus u squared. So if I do that, I'll have u squared plus 2u to the fourth. Sorry, not plus. Plus u to the sixth. So try that algebra and make sure you believe that works. That's easy to integrate, and then at the end, of course, that'll be in terms of u, but don't forget that u equals sine of x. So we can substitute back in with our sine, and we'll be done with it. So the thing that makes this work, if we really dissect it, was the fact that we had this cosine to an odd power. So that's what made everything work. So when I separated off one of those 5 cosines that are multiplied together there, I separated one of them off to go with my dx in anticipation of a substitution of u equals sine x. The fact that there was an even power left meant that I was going to find cosine to that power on this side, and I was going to be able to find a way to substitute in terms of the other trig function. So it didn't even really matter that this was an integer. This could have been absolutely anything. And when I got to this point, I would just have u to that power, and there's nothing about what I did the rest of the way that would be different. If that were u to the 1/2 or u to the -3, it wouldn't have made any difference at all. So it doesn't really make any difference what power this is, as long as this cosine was raised to an odd power. Because of the symmetry of sine and cosine, we could do exactly the same stuff if we had an odd power of sine. Then we could play the same game where over here we're trying to write even powers of sine in terms of cosine. So as long as, if an integral like this, as long as one of these powers is an positive odd number, then this process will always allow me to get the integration done. So let me just move this down so you can see what I have here. This is a table that comes from the textbook, and it gives you a strategy in general for how to integrate if you have a power of sine times a power of cosine. The only time that we can't do exactly the process that I just outlined is in this case, where we don't have either power being an odd number. And you've actually already seen one example of that. In the last homework that you uploaded, or last daily assignment that you uploaded, you wrote down the integral of sine squared, and I did the example of the integral of cosine squared. So those would be examples of something that's of this form, powers of sines and cosines, where you don't have an odd power of either one to take advantage of using this process. So we do know how to do that, and basically for any case where you have both numbers even, you'd have to do that same process, and it can be a little arduous. And since we are a sort of abbreviated semester, we won't see any complicated versions of that, but you at least have seen what you would have to do in terms of substitute using a double angle formula and so forth. All right, so that's the basic idea. On the worksheet, there's a second sheet that has 3 problems for you to try. I'd like you to go try those, and then I'll look at the second video where I work through the solutions to those 3 problems.